For today, I think I'll move with my presentation, and today I'll use my presentation fully. So, in few videos, I don't use presentations as much, but in this video, I use presentation as much as possible. So, today's topic is astigmatism, cylindrical lens, and correction of astigmatism. So, what is astigmatism and its type, and then we will go to correction. So, Latin word Stigmatus means the point. When we add a, then it's not a point form. So which is basically called stigmatism. When you add a, which is not a point, forming the line imaging of the point image. So what I wanted to tell you is, in case of optics, we have to understand if there is a spherical lens, it creates point object and point image no matter what, it's plus or minus. But in case of astigmatic lens, if lens is astigmatic, then it creates not just point but a line. If it is pure cylinder, then it creates line. If it is not pure cylinder but spherocylinder, do you know spherocylinder? I think you know. For example, plus 2 minus 3 at 90, it's a spherocylinder. Then it creates terms of conoid. I think you have heard these terms previously. So it's quite easy to understand what is astigmatism. It means basically two meridians are not in same power, they are different power, then it is basically astigmatism. So astigmatism forms the line image. When it is cylindrical pure cylinder, it forms pure line image. When it is spherocylinder, it forms circle of sorry, it comes conoid. So best point is circle of list confusion, we know it. So type of astigmatism is regular astigmatism and irregular astigmatism. So main difference between regular astigmatism and irregular astigmatism is refractive power change uniform from one meridian to another meridian in case of regular, and irregular astigmatism, irregular change of refractive power means the regular astigmatism means the two meridian separated by 90 degree. In case of irregular meridian, astigmatism, two meridian are not separated by 90 degree, which is very simple definition. So another slide is when we are talking about etiology. So what are the etiology of the astigmatism in case of eye? So corneal astigmatism results from abnormality in corneal curvature, which is main cause of astigmatism is corneal astigmatism, especially front surface of the cornea, not back surface of the cornea, but yes, definitely back surface of the cornea has its power of astigmatism approximately 0.5 in large data sample. But the main cause of astigmatism is almost and always is front surface of the cornea. So which is very important point you have to understand when you're talking about etiology. So there may be chances of lenticular astigmatism due to the abnormality of curvature of lens or due to lens tilting of the lens with the respect to visual axis. It can be happen when in a common point here to understand is lenticular astigmatism, which is commonly seen in lenticonus cases like lenticonus. And another astigmatism is retinal astigmatism due to the displacement of macula. When macula position of the macula is displaced, in that particular condition we can see the retinal astigmatism. But this is very rare condition, and this is also seen in clinical cases, but very few lenticular astigmatism. The most important is front surface of cornea. See, you can see like this. Front surface of cornea is 48 diopter approximately, back surface minus 6. Front surface of lens, okay, whatever, 10, or back surface of lens is 8. So most power resides there. And then particularly front surface of the cornea is very important. So with the rule astigmatism and against the rule astigmatism, which is very simple, when vertical meridian is more steeper, this meridian is more steeper, then it is called with the rule astigmatism. Against the rule astigmatism, when horizontal meridian is more steeper than vertical meridian. So it's basically against the rule astigmatism. So as we think in pediatric case against the rule astigmatism, when in young age with the rule astigmatism, again in old age against the rule astigmatism. We think like that, isn't it? With time this happens. So we till now. So cylindrical lenses, what do you mean by cylindrical lenses? Geometrically we can generate cylindrical cylinder by taking two parallel lines and rotating one around the other while maintaining the parallelism. The line that serves as a center of the rotation is called axis of the center, and each point of the cylinder surface is equivalent from the axis. So basically, cylindrical lens means one meridian is zero power and another meridian is uh, with the curvature. We can think like that. It's cylinder, pure cylinder means one meridian is plus minus 0 0, another meridian is whatever, minus 1 plus 2 or whatever, it is plus cylinder or minus cylinder. So basically cylindrical lenses are called cylinder because of this. If two meridian has power, for example minus 4 and minus 2, then we tend to call it as a sphere cylinder. It's essentially important to understand what is the sphere cylinder, what is, and sphere cylinder another name is toroid. So basic thing. So cylindrical lenses, the radius of the cylindrical lens, the distance from the point of the axis. For cylindrical refraction or reflecting surface, flat meridian is referred as axis meridian, and the perpendicular meridian with a cross section is power meridian. The axis meridian and power meridian are principal meridian. So basically, in case of optics, you know it already, I think, but let me tell you. Whenever we are talking about cylinder, there are two axes. One axis is power axis meridian. Power meridian means that meridian in which power resides, and another meridian where power is zero. For that case, this meridian is power meridian, but this meridian is axis meridian. So you have to understand power meridian and axis meridian. It will come later one by one, again and again. So it's really important to understand in which, in power meridian the surface has curvature, which is r. In the this meridian, axis meridian, r is always infinity, isn't it? Because see in this example, n dash minus n divided by r. If n dash minus n, whatever, n dash minus n divided by infinity means 0. So radius of curvature is infinity. In this case, in the axis, is so important to understand radius of curvature. In case of cylindrical lens, in case of cylindrical lens, not in case of toroidal lens. Toroidal lens are different things. So it's important to understand this concept. Spherical refractive error that has the same refractive power in all meridian. The cylindrical lens has maximum dielectric power in the spherocylindrical lens meridian of the maximum power, and the minimum power which are perpendicular to each other are called major or principal meridian of the cylindrical lenses. So in this case, what I wanted to tell is that, see, if here is 7 diopter and if there is 4 diopter, for example, then we can again divide it as an 4 diopter minus 4 diopter and plus minus 3 diopter plus minus 0 diopter. So together they form this, isn't it? So if you want to understand this concept, you can divide this as a spherocylinder as a sphere plus cylinder, and now it's work as a pure cylinder. Now this is power meridian and now this is axis meridian, so you don't have to worry about it. So it's simple as it. So you can split it into the sphere and the cylindrical form. So here are the few examples of cylindrical lenses. This is equiconvex lens, and this is biconvex lens, and this is planoconvex lens, and this is concavo-convex lens, which is basically what do we call that? Our spectacle has it. And equiconvex lens, biconvex lens, and planoconvex lens. Like, these are the form of convex lens. But here we are. This is the cylinder axis, isn't it, in this figure? And this is power meridian, because power meridian is always opposite to the cylinder meridian. But when this point object passes through the cylinder, it forms vertical line image. What I've already told you, in case of cylinder lens, point object forms what? Line image. It's central important to understand. So in case of spherocylinder, point object form is terms of convoid. So it's another point. And the line image is always like its axis. If axis is in vertic is 90 degree, then image formed at 90 degree. If axis is in 180 degree, then image will form at 180 degree. It's central important to understand this concept. It's very important to understand this concept. Whichever way axis is oriented, image is also oriented to the same line. It's so important to understand this concept, which is very crucial concept as we can understand in long term. Okay, so cylindrical lenses, each thin segment converges the ray only in horizontal and forms its own point image, and collectively all individual points image makes the vertical line. So why vertical line? Because vertical in vertex this axis in vertical line. That's why images also form in a vertical line. Even though the real power meridian forms vertical line image parallel to the axis. That's what I am telling, parallel to the axis meridian. It is horizontal power meridian that is responsible for the convergence of the horizontal meridian power is responsible for the convergence of light, but image forms is the parallel to the axis meridian. So if axis is vertical, then image is formed as vertical. But the responsibility of image formation, that convergence happens in horizontal meridian. That's quite confusing for first video and first books and first concept, but you will later on understand the concept when we talk about the subjective refraction and clock dial method and all these methods. The again and again comes. So the real image is always parallel to the axis. Yes, that's the point. The real image is always parallel to the axis meridian and perpendicular to the power meridian that it forms. It's central to understand, very important to understand how image forms, and real image is always parallel to the axis. So in this case, so see, this is cylinder, isn't it? Power meridian, when curvature is there, then power meridian is 5 diopter, but axis meridian is always 90-degree away from the power meridian. It's central important to understand this concept. So this is the simple thing that we have already discussed, and s minus n divided by r, which and power is simply adding one another, and image versions is power plus object versions is always there. So we have to understand the standard axis notation. It's central important when we are going to examine patient and when we're going to write a lot of prescription in our life as an optometrist. So spherical lens can be rotated clockwise or anti-clockwise around the optical axis without optical effect. So we don't have to care at all about spherical lenses. Spherical lenses, we don't care. It doesn't matter at all. You rotate clockwise or anti-clockwise. It doesn't matter. A cylindrical lens doesn't have a rotational symmetry because spherical lens has rotational symmetry. We don't care how you rotate the spherical lenses, but it's central important. The cylindrical lenses does have rotational asymmetry. So when cylindrical lenses are rotated, resulting in image rotating with it, because image is always forms in the optical axis. Hence, the cylindrical lenses is used to correct the astigmatism orientation of the lens must be specified together with power. It's always like spherical power is minus 3 DSPS, doesn't matter. You write it there and you stop. But in case of cylindrical power, you have to specify axis at correct as possible. So with vision, isn't it? So it's central important with spherical lenses. There is exact specification of the orientation. So in case of standard orientation, the coordinate system used to specify orientation is set up in terms of examination view. It's very important in terms of examination view, not by the patient's view. When looking at the patient, the view is so-called counterclock view. So when we as an examiner, not as a patient, we see the patient's eye as a counter-ocular view against the view of the patient. Each meridian will could be identified by the two different angles. Usually diopter and the degree sign are not noted because it's central important. Don't write degree signs. It's bad practice. So let me tell you, whenever there is a 5 degree, you write 005, 3 digits, not degree here. This is not an good practice. Whenever there is 10 degree, you write 010. Whenever you write 100 degree, it's 100 degree finished. Whenever you write 180 degree, it's 180 degree. Whenever you write 90 degrees, 90 degree, 090. Use 3 digits, not a dot. That's not good practice. It will create some havoc, sometimes confusion, and patient get different prescription. So it's always better to practice in writing three digits. If you are specifying axis, for example, 007, 7 degree axis, and period, it's finished. Don't use degrees here. Like some people write 7 degrees. This is bad. Sometimes we are confused with 70. So it's central important to write in three digit axis. Always write in three digit. And the axis, this is the examiner's view. We see as a patient there. So angles doesn't matter it's right or left eye. It's always from 0 degree here and 0 degree here. What? This is anti-clockwise and it moves anti-clockwise. 0, 30, 40, 50, 60, 90. It's always 100 here. It's always 150 here. It's always 180 here. It's always 180 here. Doesn't matter right or left. So it's always 30, 60, 90, 120 and all these things. It goes anti-clockwise. It goes anti-clockwise no matter what. It's right eye or left eye. Yes, it's important. We have to distinguish it's right eye or left eye. But as a practitioner, it always, zero is always on the anti-clockwise direction. Anti-clockwise direction, you move to 180 no matter what, right? In case of left eye, it's zero is nasally. In case of in case of right eye, nasally. In case of left eye, temporally. But in both eyes, same. From anti-clockwise point of view, we go from 0 to 180. It's important to understand when you say the trial frame. Definitely in phoropter, it's central important to understand. And this is the splitting, isn't it? So 5 diopter means, see, this is 2 diopter sphere and this is 5 diopter cylinder. Whenever we add 2 diopter sphere and 5 diopter, 7 diopter in the 90 degree meridian and 2 diopter in 180 degree meridian, which is very simple. And this is the pictures of Sturm's conoid, and I have already discussed in my previous video about this Sturm's conoid, so you can go there and watch there what is circle of least confusion with the interval between two focuses, which is Sturm's interval and circle of least confusion position, what is the spherical equivalent, and how we use it in day-to-day practice. We always use it in day-to-day practice of as a clinical optometrist, so you must understand this concept. So go to my previous videos, and this is the concept which I want to discuss today, and it's very important to understand the power of an oblique meridian of a cylindrical lens. Let's take an example. If in this case the 5 55 diopter power is lies in one direction. Let's take an example. This is the axis and here is 5 diopter. Obviously this is 0 diopter. So what happens if it comes here when 30 diopter? What is the power here? So for this we have to use this formula. F theta is equal to F cylinder sine square theta. So and another point is theta you must calculate from 0 degree 0 power meridian, which is axis meridian. It's central important to understand. So it's central important to understand theta from the axis meridian. So that's why, so let me tell you real quick what happens here. Whenever you, let's take an example, here is a 5 diopter, is 0 diopter. You move from here to here, power increases in a function of sine square theta. And for whenever you move from here to here, power decreases in sine square theta function. Whenever here to here, power increases in sine square theta. And whenever you move from here to here, power increases again in a function of sine square theta. It's really important to understand this concept. So lot of my student thinks that if there is a 5 diopter and if there is 0 diopter, that's it. Between these 2 points there is no power or whatever. It's not like that. Between these 2 points there are a lot of powers, but you have to understand how to calculate it. Let's take an example of 30 degree. So you must calculate how to, okay, how 30 degree, what is the power at 30 degree axis, isn't it? It's very simple, like 5 minus 5 into sine 30 whole square. What do you mean sine 30? I think sine 30 is 1 by 2, or yes, 1 by 2. So minus 5 by 4 is a power over there, isn't it? And what happens if sine 60? Sine 60 whole square is minus 5 into under root 3 by 2 whole square, which means 15 by 4, isn't it? This is the power at 60 degree. So we must understand how to calculate these things and how to understand these things. It's not zero between 5 and 0 diopter. It's There is a power variation between this point. It's centrally important to understand the power variation between this point, and the power variation depend upon the sine square theta function. So it's central important to understand sine square theta function, how it plays the role of sine square theta function for the cylindrical lenses meridian. So it's central important. So astigmatism is type. The Latin word astigmatism means we know it. It's not and point. And type is regular and irregular. We have discussed about it. Etiology we have discussed about it. With the rule against the rule we have discussed about it. And now this, the compound myopic means basically, see, in hyperopia there is only one far point. In myopia there is only one far point. Only condition there is two far point is astigmatism. So this is the far point, isn't it? This is the far point. If two far points is in front of the retina, then it's compound myopic. If one far point is at the retina and one far point is in front of the retina, it's called simple myopic astigmatism. And one far point is behind the retina and one far point is in front of the retina. It's called mixed astigmatism. One far point is at the retina and one far point is behind the retina. It's called simple astigmatism, simple hyperopic astigmatism. And one far point is behind the retina, another far point is also behind the retina. It's called compound hyperopic astigmatism. It's very simple definition. You must understand this, what these lines are. This is basically far points. So let's discuss a very little and very important points of Jackson cross cylinder, and I'll make sure that I'll make another video specifically on Jackson cross cylinder, and I'll try to explain few more things with the Jackson cross cylinder. But currently, Jackson cross cylinder just goes surfacely. Jackson cross cylinder is a combination of two cylinder of equal strength. It's very important to understand this point of equal strength with the opposite sign. Placed to the axis 90 degrees to each other, mounted in the handle of flipping. So three things is very important: equal strength, opposite sign, and with 90 degrees. And another thing is opposite side of what? Opposite sign and opposite side of the two surfaces. So it's very important to understand this concept. So sometimes you see such as equations in your examinations. So they give you, this is the power of uh, Jackson cross cylinder. Now resolve it. You don't have to worry about it. It's just a simple thing. Here is 0.50. Here is another plus 0.50. So whatever you want. Plus 1, sorry, minus 0.50 and minus 1 at 90 degrees. At, yes, 90 degrees. Then this is the answer. So there is a lot of MCQs you can see. So cross cylinder is cylindrical with lens with zero spherical equivalent, isn't it? So if you resolve this equation, is spherical equivalent 0. So spherical power of Jackson cross cylinder combines with the cylindrical power, which will twice the power of the sphere and opposite signs. Yes, isn't it? Is and the cylinder is twice the power of a sphere, which is very simple concept. So Jackson cross cylinder looks like this. I think you have seen that. And the principle is basically placing the circle of least confusion position, it remains constant. So basically, if you flip this Jackson cross cylinder, there is no change in circle of least confusion position, but there is change in size of the circle of least confusion. I'm repeating again, there is no change of position of circle of least confusion, but there is change of size of the circle of least confusion. It's central important to understand. Whenever size increase, patient see blurry. Whenever size decrease, patients resolve the optotype, patient view it clearly. So another thing, whenever the two meridian separated largely, Jackson position, okay, sorry, the size of the circle of least confusion increases whenever size of the circle of least confusion increase whenever circle of least confusion separation of the two meridian closer, the size of the circle of least confusion becomes smaller. And this is how it works, not by changing position of circle of least confusion, but by changing size of the circle of least confusion. So uses of the determine Jackson cross to determine the astigmatism. First axis, then power. It's always important to understand first axis, and then you will face it on the y first axis and y first axis, because in wrong axis there will be power, but in wrong axis there will not be exact power, as we know from this formula sine square theta. So you can explain like that. Okay, spherical equivalence is a power of a lens replaced in a spherical lens by placing the circle of least confusion. This is the concept of circle of least confusion, which is basically formalized this sphere plus cylinder divided by 2. And I hope you have to go to my circle of least confusion video. So, a patient with the correction myopia on composite hyperopia experience uniform blur when corrected with myopia and distance point source and blur. Whenever we use spherical equivalent concept, we use circle of least confusion. Okay, circle of least confusion point. So in summary, astigmatism is two focal point of two far point separated by Sturm's interval, and dioptrical center between the two foci point. The circle of least confusion is always dioptrical center, and Jackson cross cylinder is test is commonly used to determine the amount of ocular astigmatism, and Jackson of cross cylinder is very standard test too. So you have to understand. So for now, this is very important formula, and you have to understand spherical equivalent. I know you know this formula very quickly, and there are three books. I think I always tell start from this book. This is very good book, and this is my favorite and my favorite professor too, Professor George S. Melis. So that's it for today. Bye bye.